Alrighty, Chapter 14. Chapter 14 covers solutions. So we're going to be talking about gases in solutions, liquids in solutions, and solids in solutions. So the different types of solutions that we're going to see and things mixing in them. Okay, chapter handout starts with gases in solutions. So our first bullet point, the solubility of gases decreases with increasing temperature, but increases with increasing pressure. So let's look at these pictures that we have here. So in terms of our solubility of a gas decreasing with increasing temperature, so solubility is referring to like how readily something dissolves in something else, and if it even dissolves, and how much really. So the heat of our system, so the heat that we put into our system that's already in our system, is going to break apart the intermolecular forces between our gas and liquid molecules. So gas is our solute. We'll talk about the definition of solute and solvent below in just a moment. But heat is going to break apart the intermolecular forces between our gas and liquid molecules in solution, so like down below here, which means that it's going to release our gas molecules to go float back up and be a gas. So, and the pressure is going to force the gas to dissolve in the liquid. So we're going to put a lot of pressure up above, and it's going to force the gas molecules into the liquid. So that's how our soda is made. Like, we put a lot of pressure above our carbon dioxide, and that forces the carbon dioxide molecules into our water sugar solution, flavored water sugar solution. And so then we seal the can, and that gas is trapped in our liquid until we release the pressure. Once the pressure is released, our solubility of the gas is going to decrease. So pressure and solubility are directly related. So we increase the pressure, we increase the solubility of our gas, and then temperature and solubility are inversely related. We decrease the temperature, we increase our solubility. Okay, so that gas is in solution. So we'll talk about a few examples down below. But let's talk about liquids and solutions real quick. So here's our actual definition of a solution. So a solution is a homogeneous mixture with two or more components, and it's our solute dissolved in a solvent. So homogeneous means that it looks the same throughout. So it's not forming two layers, it looks like one thing. Like soda, if we have like root beer, it looks the same throughout. It's just brown liquid. Here we have our definitions of solute and solvent. So solute is going to be our lesser quantity, and our solvent is going to be our greater quantity of substances in our solutions. If we're dealing with a solid liquid solution, so we can think about it this way. We can think about our solute as the thing being dissolved. So our example here is salt. If we're trying to make salt water, our salt is going to be our lesser quantity, and it's our thing being dissolved. Our solvent in that saltwater solution is the thing that does the dissolving. Water is dissolving our salt, and water is in our greater quantity, so that's going to be our solvent. This salt and water, that's a solid liquid solution. So this doesn't really apply to our liquid-liquid solutions. So we'll think about it lesser and greater quantity with our liquids, especially. Here in our bullet points and in our table, we get a lot of examples of solutions. So the solid liquids, seawater that we were just talking about, is a type of solution. Seawater looks the same. Soda, gas in a liquid, looks the same. Alcoholic beverages, liquid, so alcohol, water. Air, gases, so nitrogen, oxygen. We got a bunch of noble gases in really small amounts as well. Blood, we got solids, gases, and liquids. So we got all three there in that solution. And then table 13.1, we have more examples if you want to look at those. Okay, next we're talking about types of solvents that we're going to see. Again, solvents are a greater quantity, typically our thing that does the dissolving. We have polar and nonpolar solvents. So if it's a polar solvent, we're going to be composed of polar molecules. Totally makes sense. Water's polar, methanol's polar, ethanol's polar. Those are your examples. Non-polar solvent, these are liquids composed of non-polar molecules. So hexane, carbon tetrachloride, ethyl ether, those are non-polar molecules. So they would make up a non-polar solvent. We need to know if our solvents are polar or non-polar, because that is going to help us determine if, like the solubility of our solutions that we're mixing. So we're going to be following this like dissolves like rule. So polar solvents are going to dissolve in one another, and non-polar solvents are going to dissolve in one another. So basically, polar is going to dissolve polar, like dissolves like, and non-polar is going to dissolve non-polar, like dissolves like. A polar substance is not going to dissolve a non-polar, just like a non-polar is not going to dissolve a polar substance. So like dissolves like. It's just one of those universal rules, kind of like opposites attract. So, like dissolves like. We need to remember that. Okay, our next two definitions that we have are miscible and immiscible. These guys refer to two solvents, so two liquids that are going to be dissolved in one another. So miscible means that two solvents that dissolve completely in one another. So they are going to completely mix. Think about miscible as mixing. So polar solute and a polar solvent. So alcohol and water, for example. Immiscible, so these are two solvents that do not completely dissolve in one another and separate into layers, so they don't mix. So a non-polar solute and a polar solvent. So for example, oil and water. Oil is made up of hydrocarbons. Those are, the carbon-hydrogen bond is not polar, so non-polar. So non-polar plus polar water. Those are not going to mix. They're going to form two layers. So in your kitchen, if you're mixing oil and water, we got two layers that are forming. Okay, let's look at exercise number 1. Predict whether each of the following solvents is miscible or immiscible with water. So is it going to mix and form one solution, or is it going to be immiscible and form separate layers? So our first one that we are looking at is methanol. So CH3OH. So the carbon-hydrogen bond here is nonpolar, but the oxygen-hydrogen bond and the oxygen-carbon bond is polar. We got a hydrogen bond here. It's definitely polar. So methanol is a polar molecule. Alcohols are polar. So water is also polar. So we have a polar water mixing with polar methanol. So like dissolves like. Since it's polar, therefore they are miscible. Polar, therefore they are miscible. Let's look at letter B. It's down below. Okay, so we got toluene. C7H8. We just have carbon hydrogens in this molecule, which means the carbon-hydrogen bond is nonpolar. So this is a nonpolar molecule. Therefore, it is not going to mix with water. So like dissolves like. If it is not like dissolves like, it's going to be immiscible. So nonpolar, therefore immiscible. All right, let's turn the page. Here we're talking about solids and solutions. With solids and solutions, we are using the terms soluble and insoluble. Is our solid going to dissolve? Is our solid not going to dissolve in our solvent? We're still following like dissolves like. So here we have a table. So we have a solid solute, polar solvent, non-polar solvent. So in this first row, we're going to have a polar solid solute. A polar substance is going to dissolve in a other polar substance. So polar, like dissolves like, we're soluble. Polar and non-polar are not like dissolves like, so insoluble. Non-polar solid solute and a polar solvent, they are not similar, not both polar or non-polar. Insoluble, it's not going to dissolve. But non-polar and non-polar, like dissolves like, we are soluble. With this third row, notice how ionic is soluble in a polar solvent, but insoluble in nonpolar solvents. This is due to our dipole moments that we see in ionic, in our polar solvents. So with ionics, we are forming fully positive, fully negative charges. So for example, sodium chloride. It's going to separate into positive cation sodium and anion chlorine. Those positive and negative charges are going to be attracted to the dipole moments in our water molecules. So oxygen is more electronegative than hydrogen is. So we're going to see a partial negative charge on our oxygen and partial positive charges on our hydrogens. These partial positive, partial negative charges are going to be attracted to these fully positive, fully negative charges. So opposites are going to attract there. So that is why ionic solutes are going to dissolve, be soluble in polar solvents because of those dipole moments that we see there. All right, let's look at exercise number 2. So exercise number 2, we're predicting whether each of the following solid compounds is soluble or insoluble in water. So fructose, C6H12O6. Notice it has the same molecular formula as glucose. It's just got different structures, if you're curious. Okay, so carbon-hydrogen bond, nonpolar, but we got oxygens in the mix. And typically with big compounds, like molecules like fructose, glucose, and sucralose especially, we don't have perfect symmetry. So these polar bonds, the polar carbon-hydrogen bond, polar carbon-oxygen bond, is going to mean that we have a polar molecule. So polar molecule, we actually have hydrogen bonds present. So water is polar. So we got a polar thing dissolving in another polar thing. So that means it is soluble. Fructose is soluble in water. Letter B, we got lithium carbonate. Lithium is a metal. Carbonate is a nonmetal polyatomic ion. If we have a metal involved, we are an ionic compound, which means that if we are in a polar solute, we are soluble because of the partial positive, partial negative charges being attracted to the fully positive, fully negative charges. So we are ionic, and therefore we are soluble in a polar substance. For letter C, we have naphthalene. C10H8. We only have carbons and hydrogens, so we're a hydrocarbon. Carbon-hydrogen bond is nonpolar. So nonpolar molecule, which means we are insoluble in a polar compound or polar substance solvent such as water. All right, so our next topic that we are going to talk about is the dissolving process. So when we have substances dissolve in water, for example, we're going to be forming a solvent cage around the ions that form in solution. So a solvent cage, our molecules are held within a cluster of water molecules in solution. So this will happen with like salt. This is going to happen with like sugar, glucose. They're going to be surrounded by water molecules. And how that is going to happen is our water molecules are going to surround our ions. So the partial positive side of water is going to surround our anion. So for example, sodium chloride. So we're going to form sodium cation and a chlorine anion. And the partial positive side of water is going to surround our anion. So that partial positive side is our hydrogen. The hydrogens are going to be attracted to the negative chlorine. And so water is going to orient itself because of the attractive forces between our cation anions and these partial positive and partial negative charges. Likewise, for our sodium ion, the partially negative oxygen is going to be oriented towards our sodium and just surround the entire molecule. So I'm only drawing two water molecules of each surrounding each of these, but there's actually a lot more. So like, for example, in these pictures, we got 6, but I don't want to draw 1,000,000 water molecules. So partial negative charge is surrounding our positive, our cation, and then the partial positive charge of water is going to surround our anion, the chlorine. For substances that that are dissolved in water this way, we call them hydrates, that they have water molecules attached. When we were doing molar mass of substances, you might have seen something like sodium sulfate, and then you might have seen something that looks like a multiplication sign, and then water. So this means that water, 10 water molecules are surrounding that molecule there. So we call these hydrates. We got water attached or water surrounding, especially in solutions. Do we see this? Okay, so our rate of dissolving is going to be affected by 3 things. So 3 things are going to increase our rate of dissolving. So these things, heating a solution. So heating a solution breaks apart the solute-solute bonds, because heating a substance is going to make our molecules move a lot faster. They're breaking away, moving away from the molecules around them. So solute, like intermolecular forces, instead of bonds, really. Stirring the solution, so we're allowing more flow for solvent interactions, more opportunities for contact and interaction. And then our third one is grinding our solid solute into smaller particles. Basically, this is creating more surface area to volume ratio. So for example, a big sugar cube is going to dissolve a lot slower than powdered sugar. So because we are grinding it up, for example. So those 3 things are going to increase our rate of dissolving. So heating a substance, stirring the substance, and grinding the solute. Okay, next we're talking about solubility and temperature. So solubility, here's your actual definition in the chapter handout. So solubility is the maximum amount of solute that can be dissolved in 100 grams of water at a given temperature. So we are going to be looking at solubility curves. So solubility curves have a bunch of different substances that are going to be portrayed in our solubility curve. Basically, on the y-axis, we are looking at solubility of our solute, so grams of solute in 100 grams of water. On our x-axis, we're looking at temperature. So notice how for all of these substances, as we're increasing our temperature, our solubility, how many grams of that solute are going to dissolve in water. We are increasing how much is going to dissolve in the same amount of water. So let's look at exercise number 3. So determine the solubility of each of the following compounds at 50 degrees Celsius, as shown in the figure above. So we're using this solubility curve that we have here. So we are looking at sodium chloride. So we want to find sodium chloride's curve. So it's this guy right here. And we want to see how much, so amount in grams, at 50 degrees Celsius. So how much in grams is going to dissolve at 50 degrees Celsius in 100 grams of water. So here's 50 degrees Celsius. I've highlighted it in this blue color. And I'm coming up to where the 50 degrees Celsius line crosses my sodium chloride line. And that is right here. That looks like it's about like 36, 37 grams that's going to dissolve in 100 grams of water at 50 degrees Celsius. So I'm going to say like 37. Why not? You might have said 36, you might have said 38, that's fine. And then we're looking at calcium chloride. So still 50 degrees Celsius, but we're going to see the solubility of that guy at 50 degrees Celsius. So sodium chloride is this line right here. So at 50 degrees Celsius, that's the point that crosses my 50 degrees Celsius line. So that looks like it's about like 42 grams in 100 grams of water. So 42 grams of sodium chloride is going to dissolve in 100 grams of water at that temperature. So now that we know how to read a solubility curve, we need to talk about what the line means and what else do we know from looking at that graph, at that curve. So we got 3 definitions at the bottom of this page. Our first definition is we have a saturated solution. So a saturated solution is a solution containing the maximum amount of solute at a given temperature. That is the line in your solubility curve. This is the maximum amount of solute that is going to dissolve for sodium chloride at any temperature. So it's changing with temperature, and it all depends on our temperature. So this is our line, our curve. So this is the curve / line. Our next definition we have is unsaturated solution. So an unsaturated solution means that we can add more solute and it will dissolve at any given temperature. So this is any point below our curve. So let's take, for example, our sodium chloride that we did. So our saturated solution would mean that we have 37 grams of sodium chloride dissolved at 50 degrees Celsius. That is saturated. We cannot add any more. It's not going to dissolve. But anything below our curve, so if I added 20 grams of sodium chloride into water, we're still below our curve. We have 17 more grams that we can dissolve in our 100 grams of water. So anything below our curve is considered unsaturated. We can add more and it will dissolve. So if we had 36 grams, we could still add another gram and it would dissolve. So anything below our curve. All right, and last one, our supersaturated solution. So supersaturated solution is a solution that contains more solute than ordinarily dissolves at a given temperature. This is any amount above our curve. So still taking sodium chloride, our saturated amount was this 37 grams. Our unsaturated solution, anything below 37 grams. And our supersaturated is anything above our curve. So if I added 100 grams of sodium chloride to 100 grams of water, we are super saturated. But even if I added 38 grams, 39 grams of sodium chloride to our water, that extra 1 or 2 grams is not going to dissolve. It will be left as a solid. You will be able to see it in solution, probably at the bottom of your beaker or whatever. Saturated and unsaturated solutions look the same to us. We're not going to be able to see any solid in our beaker like we would supersaturated solutions. So saturated and unsaturated visibly to us look the same. It's only until we get to supersaturated solutions that we can actually see that something's different. All right, so let's look at our exercise number 4. So at 30 degrees Celsius, give an example of a sample of potassium chloride that is saturated, unsaturated, saturated, and supersaturated in 100 grams of water. So we are going back to our solubility curve. So we want something that is saturated. So we are looking at potassium chloride, so that's this KCl, and we are looking at 30 degrees Celsius. So my 30 degrees Celsius is down here. So I'm going up to where I hit the line, and that's this guy right here. So that is about like 35 grams. So 35 grams is our saturated line. That is how much is going to dissolve in solution. We can't fit any more with it still dissolving. All right, so our unsaturated now. Unsaturated is literally anything below our line. So our line is here for 30 degrees Celsius, so anything less than 35 grams works. So I randomly chose like 20 grams, but it's anything less than 35 grams works. Supersaturated, so that is anything above our line, anything above 35 grams here. So any amount up there. So for a supersaturated solution, this is anything above 35 grams. At this point, you can do the solutions worksheet. And it's using just everything that we talked about at the beginning of chapter 14.